Thanks to having this conference and organizing it for us on higher or categorical representation theory, a topic that's near and dear to my heart. So I know it's late. We have some people maybe a little jet lagged, so we'll try to keep it a little chill, relaxed. So what I want to talk about today is sort of maybe new or newish direction in categorical representation theory that was inspired from knot theory. And this idea about having intersections between topology and categorical representation theory, I think it goes back quite a ways. Like, this has always been a source of inspiration in categorical representation theory, taking ideas from knot theory or things that people are seeing in linked homology theory, that are thinking about what they mean in the world of representation theory or categorical representation theory. And so that's part of a story that I want to tell you about today, is how some ideas in linked homology impacted things to do with categorical representation theory in such a way that at the end of the story, we're going to be talking about modular representation theory of the symmetric group and proving some new theorems. But the story starts with thinking about knot theory. So, there's a famous, pretty well-known story to probably many in this audience with Kleshchev and Livesey. I could have left myself more room. All right. It is late. I understand. So there's a close connection between Kleshchev homology and the categorical rep theory of quantum SL2. And sometimes we'll say like categorified quantum SL2. And I'm gonna, anytime I talk about something categorified, I'll use a curly script so you know when I'm talking about that. So categorified quantum SL2, I'll use this curly script when I mean. So there's this nice intersection between Kleshchev homology and categorical representation theory. Of course, this is just a categorified version of an older story that's much better understood between the Jones polynomial and the just normal quantum SG2. So SL2, sorry, I've been talking to physicists too much. So, of course, the story here is that this is the braid Euler characteristic, or in other words, Kleshchev homology categorifies this old knot invariant. And over here we have more exotic notions of decategorification, where we're taking the split growth of the ring or something like this. So this is a nice story. It's kind of cool. There's like from representation theory, we can understand these knot invariants. But the part of the story that I think is the most exciting and interesting, and part of why there's probably so much interest around this area, is that this world of linked homology theories actually brings in a huge swath of mathematics, right? I mean, we have things like flag varieties, things to work with like at least Katarina and Ben. There's like Springer varieties, probably lots of others. There's of course like symplectic approaches to Kleshchev homology. So there's symplectic approaches. We have matrix factorizations. We have affine Grassmannian. So if you like algebraic geometry, you can think about Kleshchev homology. And then that's not even all. I mean, there's like there's nice, cool, like Fomes description, or like in the Kleshchev homology, it's kind of like 2D TQFTs. And you don't need to know all these words. This is just to show you, like, there's a lot of words in this world. That's not even the physics one, right? Like in physics, we have like BPS states, and we have supersymmetric Yang-Mills theory. So you can kind of see why people are, knot theory is a place where lots of worlds come together, and that's what makes this area so exciting. So you can imagine how the story was looking like back in around 2007, when people discovered that there was a new guy in town that was doing many of the same things that Kleshchev homology was doing. In other words, it was categorifying the Jones polynomial, but it was somehow different. So in 2007, Rasmussen, Ozra, and Savo introduced something that they called odd homology. And so it was quite interesting to see that.
Let's stay.
Okay, I won't right below it then. So both of these things categorify the same classical invariant. So they're both categorifications of the same thing, but these theories are inequivalent. So each of these theories can distinguish knots that the other one can't. So they're not the same invariant, but they categorify the same thing. So this is kind of exciting, well, because now we're kind of seeing like what the categorified world has to offer. Somehow we can categorify things in two different ways. And what's especially interesting, though, to me, is that they actually become the same when you reduce coefficients mod 2. So inherent in this odd world, if you've ever looked at the definition of Copenhagen homology, it's not important if you haven't, but one of the ways that you kind of define it is using these cobordisms, two-dimensional surfaces, and you use TQFTs basically. And basically, in the definition of odd Copenhagen homology, it's very similar, except for when you slide handles past each other that you would normally do in two-dimensional TQFT, you just pick up signs. So it's like your two-dimensional cobordisms have some Morse function, and when you exchange the heights at critical points, you pick up minus signs here and there. So it's just like a very weird tweak to the definition. But at the end of the day, you get this like totally different link homology theory that can tell apart different knots that Copenhagen homology couldn't. And so if you're Misha Kovanov, you look at this and you start thinking like, well, let's figure out what representation theory has to say. So this was back around 2011, postdoc there, Alex Ellis was a grad student, and the three of us started trying to figure out how to give a representation theoretic understanding of this new stuff that we were seeing in link homology. There's actually a lot of other good reasons why trying to do that is an interesting idea. Partly, I don't want to go too much into it, but odd Copenhagen homology has a nice relationship with Ebert-Fleur homology. There's some nice spectral sequences there. And there's some hope that maybe those spectral sequences can also be understood in terms of categorified representation theory. In particular, there's some extra DG structures which exist here, but I don't want to make the talk, this is supposed to be the nice part of the talk, so let's not go too much into that. Just to say, there's some good reasons to think that representation theory may have some nice things to say. And it turns out, and you might also ask yourself, well, okay, if we're successful in doing this, getting some kind of odd representation theory in the story, how much of the rest of this world has a weird, odd version of it? Some kind of skew commuting or not commutative anymore version. And the shocking thing is a whole lot. So that's what this talk is about. I want to tell you about this like odd world of Copenhagen homology. And I'm really trying to address two audiences in this talk. So for the first half or whatever's left, I want to talk about, just give you like a big picture. I'm not going to go into the details. I'm just going to give you like the highlights of odd world to sort of pique your interest in this weird world. And then in the last half, I'm going to tell you what's new. So we've been developing this theory since 2011. And very recently, we've sort of culminated this theory into some new tools, which allow us to prove some new results about the symmetric group, spin symmetric group. So I want to make sure to tell the experts and the people that know a little bit about this, some of what's new and how this theory actually translates into stuff that other people who don't say categories might care about. Any questions? Feel free to interrupt. Yeah.
Is it known whether homology is an architecture?
I think it is. I think it is because it's connected to like instant homology. I'm pretty sure that's it. Is that right? Kevin is nodding your head, so that comes. I didn't just make that up. Okay, so what I want to do is, not everybody knows all this story about like luckily Ben gave from what I hear, a really great introduction to a lot of categorical SL2. I know everyone wasn't fortunate enough to be here to hear that. So what I'm gonna do is just give you like a quick recap of some of the structures which are important in the normal story, and then tell you how they get weird when we start doing this odd stuff. Okay, so let's start with like even normal. So I'll say normal is like even and weird is the odd. So even structures. in categorified SL2. So these are things that are important when you start to look at the structure of categorified SL2. So the first thing that's important is the theory of symmetric function. You know, when this plays a role in sort of many different ways, but it's very basic topic, right? A lot of people think about symmetric functions beyond representation theorists or categorification lists. I'm just meaning regular old polynomials that are invariant in the symmetric defection. So this has a nice algebra structure. There's all sorts of cool things we can say about this, but like let me just highlight that it has like nice bases of say elementary, complete, sure functions. So there's all this nice combinatorics associated with symmetric functions. So for example, we know one of the things we know is that this thing is a polynomial ring in these, I'll use this notation for elementary, this notation for complete symmetric functions. So it's you know, the polynomial ring in these symmetric functions, or the complete schema basis. And if you don't know these elementary symmetric functions, they're like pretty easy to define. So like EI is like the sum I1, I2 of let's say I less than or equal to n of x I1. So for example, if n equals 3, you get something like E1 is like x1 plus x2 plus x3, E2 is x1 x2 plus x1 x3. Okay, maybe, I mean, we all know, many of us know symmetric function theory. I'm just trying to remind you of some of the cool, or the main players in this world. So the surprising work that, one of the first things that was shown in this, so Michael and Ellis studied this ring as a Hopf algebra and saw that there's actually this weird parallel world, which also ended up, we studied later in some later work. I'll tell you a little description about that in a minute. But there's this new thing called odd symmetric functions. And the thing that's weird about it, so in all the stories that I'm going to tell you today, I want you to keep this example in mind where they're different, they're distinct theories. When you reduce coefficients mod 2, they become the same. But there's somehow some kind of weird non-commutativity or skew-commutativity in the odd world. So these odd symmetric functions are a non-commutative ring. They're not even super commutative, it's just a non-commutative ring. But it has like all of the same combinatorics that you see with regular symmetric function theory. So this has odd analogs of elementary, complete, and sure functions. And what makes them a good odd analog? Well, when you read coefficients mod 2, they're the same. You know, there's nice relationships between elementary and completes. There's a similar thing in this odd story. Odd sure functions have a similar, like, Jacobi-Trudy-like formula. But this ring is genuinely non-commutative. So let me just come to one example of, like, just exactly where you can see what's weird about this. In this ring, you have a relation like epsilon 1, epsilon 2 is epsilon 2, epsilon 1. It's a commutative ring. In this world, it's not even that this is true super. You get a relation like epsilon 1 plus epsilon 2, epsilon 1 is 2 epsilon 3. So this is what I mean, it's like it's not commutative. But you can see exactly like when coefficients are reduced mod 2, that's just the same relation. So this is the kind of sense in which this thing is kind of weird, in like a weird, but it has like all the very similar combinatorics. And so you just keep pushing down this rabbit hole, and like we're going to keep seeing like more and more of the familiar things having this kind of non-commutativity, reducing mod 2 while still having like very similar combinatorial relationships. I think it's actually a plus. Is it mine? So I think it's
Up to modules to that matter, right?
yeah, up to plus. It's a, I'm not sure.
It's the same.
It's not even the same. Yeah, they're the wrong sign, and then it's also about 2. Like if they had the wrong sign, that would just be like, oh yeah, they skew commute instead of mu. I think it's, yeah, I think it really is a plus sign. I'll show you a way in a second to figure it out in pretty fast. Because when Alex and Michael were studying this, they were thinking in terms of just like actual Hopf algebras, where these are like different generators satisfying different relations. In a second, I'm going to tell you how to think about them as being like actual polynomials. Right. So another thing that's very important in this theory is the ring of polynomials. It's a Hopf algebra, yeah. Yeah, that was part of the cool thing that Alex and Michael showed, was that it has nice. Basically, there's like a bilinear form where you can kind of count, like the way you can normally compute the bilinear form is you like count intersection points. And Michael observed that if you count each crossing with a +1, this is the inner product that you get here. In general, you can count it with a q. And if you set q equal to 1, that form has a nice radical, which you can actually write down. And that radical of that form is exactly the odd symmetric function relations. But we give a completely different description about symmetric functions in terms of certain polynomials. Yeah. So some things that are important for polynomials, especially if you're trying to understand categorifying SL2, is that this guy is a free module over symmetric functions with bases. They call them like staircase monomials, like where you go L1, where these each of the LIs is sort of bound by n-i, so they kind of like decreasing as you go down. There's another important basis, which is the basis of Schubert polynomials. So these are indexed by W in the symmetric group. You have this Schubert polynomial basis. And so again, you can see both of these things have size n factorial. So this guy is a free module over symmetric functions of size n factorial. And again, that just means like I can write any polynomial as some symmetric function times either one of these polynomials or these, or so these are basic. Okay, so the analog of polynomials in this odd world is called odd polynomials. You know, you could have just called them skew polynomials. So you take the free algebra on these generators and you mod the relations xi, xj equal to minus xj, xi, if I is not equal to j. And that last condition is actually really important, because if I allow I to be equal to j, this would just be the exterior algebra, and it would be super commutative. But this fact that xi commutes with itself and skew commutes with everything means that this ring is not commutative. It's not super commutative nor commutative. Not commutative or super commutative. Okay, and you guys are probably not super surprised that if we set coefficients mod 2, these are the same. But what's interesting is that we can also show that this guy is free over these odd symmetric functions with basis the staircase monomials. Staircase, so x1 and L1. And with we can define an odd analog of Schubert polynomials. And my story is a little bit backwards here, because to explain what I mean by that, I think of the Schubert polynomials being defined using divided difference operators. And if you write down a formula for them in terms of divided difference operators, it is something like probably like this W inverse W0 on. I think this is the definition that most people are used to seeing. So you take this decreasing, I don't know if that's the definition I'm going to be doing. So the point is, we're going to see that there's actually an odd analog of these divided difference operators. If you write down literally the exact same formula, you get a definition of odd Schubert polynomials. Those odd Schubert polynomials happen to be a basis of this thing with free of rank the same rank. Okay. You might be thinking like, yeah, okay, you're just doing a lot of weird stuff, but the thing to keep in mind is that like on the odd world, everything is non-commutative, but it's still doing the exact same kind of combinatorial relationships that we have with the even theory. And the fact that like it keeps going, the connections, it's like, it tells you it's actually something kind of more deep, not just some odd coincidence. Unintended. So is there any questions up to this point? Yeah.
Is it a Frobenius extension?
Yeah, I think John and Sasha just proved that.
Ah,
Yeah. So by the way, let me give you an example. So one of the things that's true is here, actually, let me just give you an example. Because Alex and Michael were thinking about this as an abstract Hopf algebra, but here I can actually write down for you as some skew polynomials what these odd elementaries are. So the odd elementaries, you just take that exact same formula that I wrote over there. And you put a twiddle, where xi twiddle is -1 to the I-1 xi. So for example, E1 would look like x1 minus x2 plus x3. E2 would be like minus x1 x2 plus x1 x3 minus x2 x3. So they're like very concrete, like I can write them down and it's kind of telling you, well, there's some minus signs, but they, when you start skew commuting them, you get this relation here. They're not the one where they skew commute. So here's like a concrete realization of this Hopf algebra as actual skew polynomials.
What actually is the symmetric polynomial set?
It's a good question. So how do we define it? Let me answer that by going on, and I'll tell you exactly in a second. Any other questions?
Yeah, I guess I have another question.
Yeah.
So the symmetric function, usual symmetric functions are generated by the primitive elements. They're generated by the, oh, well, I guess over Z, maybe not. But they, anyway, you have these.
Yeah, they're not generated by power sums over Z.
Yeah, right. But anyway, there are power sums.
Yeah,
Are there odd power sums?
I think so. I think so. They haven't played as much of a role because everything's integral normally, and when you, a lot of what we do is reduce mod 2 to make arguments.
Yeah.
So I need for them to be a basis of a Q. But it's a good question. I don't remember them playing any specific role so far in their theory.
Is there an analytical difference?
Yeah. That's due to maybe just Alex and Michael. There's some like extra combinatoric on Tableau that you count, and it helps you figure out the weird squares that show up. Okay, so another key player in this story is the Nil-Hecke algebra. Maybe Ben talked about that last week. So this algebra, NHN, it has generators, these polynomial generators. So the polynomial sits inside here, but we also have these divided difference operators. And relations like xi, xj, xj, xi, it's a polynomial ring. Partial I, partial j is partial j, partial I. Oh, that's if I is not equal to j. All right, I guess it's so. Partial I squared is 0.
Plus or minus 1.
What's that?
I not equal to J. Plus or minus 1.
Oh, yeah, thanks. That's right, yeah, sorry. I'm just writing what's quickly. And then the most important relation is how the divided difference operators interact with the polynomials. You get this relation like this. So this is sort of the more interesting relation. You have braid relations too, like this. Okay. So this algebra acts on pole n, where xi is multiplication by itself, and these partial i's are these so-called divided difference operators. So if f is a polynomial, I can do f minus produce the variables xi and xi plus 1, divide by this. It doesn't look like it's necessarily a polynomial, but this is a polynomial. It'll end up being symmetric. And this is a nice action of the Nil-Hecke. This is actually a faithful action of the Nil-Hecke algebra on polynomials. An important fact for us is that so fact, can you see this low or is it? No, okay. So fact, the Riemann symmetric functions is actually isomorphic to the kernel, the intersection of the kernels of all over I equals 1 to n. So if you look at all the polynomials which are killed by all these divided difference operators, that's exactly the ring of symmetric functions. It also happens to be exactly the same as the images of all these divided difference operators. So if you apply all these divided difference operators, the polynomials which are in the image of all of them are symmetric polynomials. And the same thing, the polynomials which are killed by all of them are symmetric polynomials. So when I come over here and tell you about the odd theory, as soon as I can define what an odd divided difference operator is, you might have a guess for what the definition of odd symmetric functions should be. And that's pretty much what we did. Let's start. What time do you want me to end? Let me see that. I'll end whenever. Was it?
In 20 minutes.
In 20 minutes. End. Got it. So the odd Milbeck algebra. So what we'll do is we'll just stick an O in front of everything. Odd Milbeck algebra. Basically, it has the same generators except for xi and xj skew commute. So it has this odd polynomial ring inside there that's skew polynomials. It also has these divided difference operators, but now they skew commute. It still has partial I squared is 0, still has a braid relation. But in typical, can't believe that's a new paper fashion, we take the sign here and turn it into a plus sign. You get xi partial I plus xi plus 1 partial I equal to 1. And you write a whole paper about it, but so yeah, so let's see what else is over here. Okay, so this thing acts on those odd polynomials with xi multiplication. The definition of the odd divided difference operator is a little bit more tricky. One way I gave you this nice formula here that makes it kind of obvious how it works. Another way you can kind of deductively define it by saying partial I of xj is 1 if I equals j minus 1 if I equals j plus 1 and 0 otherwise. So you can just convince yourself, like if I plug in xi here, it's xi, the symmetric group, that becomes xi plus 1, xi minus xi plus 1 divided by the same thing, that's plus 1. And if I did it the other way around, I would get a minus sign. And if I did it with anything else, I would get a 0. And then you can like inductively define it by saying partial I of f minus g, partial I of f, leave g alone, plus act by the symmetric group on f, and act on g. So this is sort of Leibniz-like rule. So basically here is you just do the trick of changing some minus signs to plus signs. So you can define it by the same thing except for it's 1 if I equals j or j plus 1 and 0 otherwise. And then there's a similar Leibniz-like formula that you can extend it by. And you can show that that's actually a faithful action of this odd Milbeck algebra on odd polynomials. Then you can define O lambda n as the intersection of the kernels of all these divided difference operators, based on the intersection of the images of all these divided.
Sorry, just to double check. It's the same. It's the same line.
It's the same Leibniz rule except for the SI actually is different. I should probably call it that. I'm gonna hide all the any detail that's. But yeah, there's the same Leibniz rule except for it's this the SI acts by the sign representation. So you extend partial I FG is the same thing. Except for SI of F is defined by It's this, I don't want to write it down, but it, like every xi gets a minus, so it's this sign version. So there's extra signs in this Leibniz rule. Okay, but what's important? This gives you a faithful action of the odd and negative. You get this odd symmetric functions. We already have that odd symmetric functions are free. Odd polynomials are free module over odd symmetric functions. So in the normal case, this is how you actually categorify the positive part of SL2. So the theorem, the Neal-Heck algebra, if I take the direct sum of these Neal-Heck algebras, this categorifies the positive part of SL2. If you remember, SL2 is like E, F, and H, and have these relations. So categorifying the positive part, that's like E. Is it really hard to do that? I mean, the only thing that you really want to see is this notion of a divided difference operator. You want to see something which is isomorphic to n factorial copies. Sorry. There's a divided difference operator, and when you work integrally, the E divided power n is just the normal n where you divide by quantum n factorial. So you need some object which is isomorphic to n factorial copies of some other object. But the fact that the Neal-Heck algebra is acting on polynomials, we get a map into endomorphisms of polynomials. This was a faithful action. And because polynomials are free over symmetric functions, this is just some big matrix ring, size n factorial, with coefficients in lambda n. And in fact, you can prove that this is an isomorphism. So the Neal-Heck ring is just a big matrix ring of size n factorial with coefficients in symmetric functions. So in particular, if I take the regular representation, that thing is going to break up into n factorial copies of this column representation. That's your categorification of U plus. Okay, I went a little fast there, but this divided power relation is really key. And it comes from this fact that the Neal-Heck ring is this matrix ring of size n factorial. So over here, we get exactly the same thing. So odd Neal-Heck ring, we just showed an active endomorphisms of odd polynomials. Odd polynomials are free over odd symmetric functions of size n factorial. So we get the same thing. And so you get the same thing that this categorified U plus also. So we have two different categorifications of the positive part. So if you heard about the KLR or Rouquier-Heck algebra, the Neal-Heck algebra is like the first example, the SL2 analog of the KLR algebra. And now we're seeing that the rank 1 KLR algebra has an odd analog, which also categorifies the positive part of SL2. So now we have two different odd symmetric functions, two different odd polynomials, two different Schubert polynomials, two different Neal-Heck algebras. This whole world is like parallel, but as you can see, this algebra is like very non-commutative where this thing used to be. And it's all because of these few polynomials which commute with xi commutes with itself, but it doesn't commute with the others. It just keeps going. So over here, there's another cool fact that you can define this, what's called a cyclotomic quotient. So let me say definition. If we define a cyclotomic quotient of the Neal-Heck algebra, say n lambda. So this is where you just quoted by x1 to the lambda equals 0. So you're killing x1 to some power. This is what we call a cyclotomic quotient. And if I take the direct sum n bigger than 0 of these cyclotomic quotients, this actually, I'm going too fast now. One can show that this cyclotomic quotient is actually, when you do this quotient, you still get this matrix ring of size n factorial, but when you see what happens, you're actually killing something in symmetric functions, which makes this the cohomology of a Grassmannian with coefficients. Sorry, okay, this is n lambda manipulation here. Let me use big N here. I'll get myself confused. I'm switching manipulation on the fly. So they have these cyclotomic quotients which turn out to be related to cohomology rings of Rachmaninoffs. And this is actually how one can categorify irreducible representations. So if you look at these cyclotomic quotients where you sum over n, this is isomorph. This categorifies highest weight rep of SL2, the highest weight n. So what I'm trying to say is like this Nilheka story is kind of, there's a lot of stuff going on here. It connects to a lot of classical objects, like we're seeing cohomology of Rachmaninoff. So then over here, you might be saying like, okay, well, let's just define this odd difform quotient to be or this odd cyclotomic quotient to be the same thing. And what do you get? You get the definition of some new non-commutative ring that you might be tempted to call the odd cohomology of a Rachmaninoff. O H star N. And that thing is, this thing here is non-commutative ring. It has shockingly similar combinatorics to the normal cohomology of Rachmaninoff. So for example, in the normal theory, there's a basis for the cohomology of a Rachmaninoff given by Schur functions, which fit inside a k by n box. This new non-commutative ring has a basis of odd Schur functions, which fit inside a k times n box. Except for it's a non-commutative ring, and we have no idea what odd cohomology is. It's just some algebraic construction producing a non-commutative ring that agrees with a normal cohomology ring, and the coefficients are reduced mod 2, but is somehow inherently different. So this guy also categorifies the highest weight representation by for the same reason. Okay, so we have Nilheka algebras, polynomials, symmetric functions. The next place that the story went was to categorifying the whole part of quantum SL2. And I think Ben started showing you a little bit of the structure, but even for a board like this, it's probably too much to get into the guts of what the full categorification of quantum SL2 looks like. Let me just sort of tell you that.
Sorry, can this be realized as partial invariance in your polynomial system?
Wait, sorry, say it again more time.
So the cohomology ring of the cosmetic can be realized as a quotient of partial invariance.
It's like O lambda n mod h1 to the n, I think. Is that what you mean? Or
Okay.
No, it should be co-invariant.
okay, so it's not okay. It is not some invariance under some Sn action, and that's the thing that there does seem to. I'll tell you a story in just a second that maybe suggests what it should be. I think it should be related to the Hecke algebra cubed with -1, possibly. Because I'll just say a few more things and then we'll come back to this. So even we can categorify full quantum group. For SL2, and you can do the same thing with the odd. This was due to Alex Ellis and I. So that's checked. You remember on this board I had a whole world of connections to Covenant homology. Another was the cohomology of Springer varieties. And of course, these cohomology of Springer varieties, like a geometric interpretation of the spec modules for the symmetric group, they have an SN action. We can do some sort of like understanding this very combinatorially and translating all the things over into the odd world. We have odd Tamasaki ideals, odd Garcia-Corchesi modules. We start messing around here. We get odd cohomology of Springer varieties. And these things get actions of the Heck algebra Q equals -1. So you get the spec module for the Heck algebra Q equals -1 instead of the spec algebra for the Heck algebra at Q equals +1. So that's kind of weird. I mean, but it just keeps, this is I should mention this was with Heather Russell. And then the new part, if you keep going down the even story, the biggest, like, the coolest thing is these derived equivalences that Ben talked about last week. Those are the things that like make this categorified stuff famous when Chuang and Rouquier used these guys to prove the abelian defect conjecture, which is a statement that is just purely about the representation theory, the modular representation theory of the symmetric group. But what they do is they use this categorified rep theory to build these derived equivalences. And in order to do this talk really quick, I'll just say that's what's new. We did that. Just to give people credit where everyone is credit's due. So, okay. You can write down the natural analogs of these derived equivalences. It's not that hard once you understand how to categorify this UQSL2, do the odd version of that. You can write down some complexes which look just like the normal complex. What's hard is to prove that they're equivalences. In the even case, there's two ways to do that. Chuang and Rouquier's original approach uses these things called minimal categorifications. That works in an abelian context. And then later, there's a more refined version due to Rouquier, and later his grad student Laurent Vera kind of enhanced it. And there you can work in the additive setting. In the case of like, basically you're building some like very primitive or like the basic building block of any two representation in the two different settings of added or abelian. What they are is, in the even case, one is built on cohomology rings across modules, where you build certain bimodules that come from two-step black varieties. And one is built on what are called deformed cyclotomic quotients. So instead of quotienting by x1 to the n, you quotient by x1 to the n plus some variable times x1 to the n minus 1 plus x. And that's actually, if you follow that deformed quotient through, instead of having the normal cohomology of Grassmannian, you have the equivariant cohomology of Grassmannian. So the stuff that's new is that, so you could also do that deformed cyclotomic quotient, do the same thing, and try to construct a two representation there. And basically, this theorem that I'm talking about has been proven by independently. So Laurent and Kleshchev proved this. And these guys and me, Ebert, Ellis-Khovanov-Lauda, Vera, and we put our papers out on the same day. They're very complementary because exactly Laurent and Kleshchev developed this odd cohomology of Grassmannians, odd equivariant cohomology of Grassmannians, odd bimodules, these things. And we do the odd deformed quotients. So this is more for the expert. We developed the odd quotients. So ours works in the additive setting, theirs works in the abelian setting. They actually had to do way more work because these odd bimodules, everything's super and it's kind of a mess. But using work of people like Kang, I feel bad if I want to mention these guys. So Kang-Kashiwara-Tsuchioka did a bunch of work that related this kind of. These guys actually invented the odd Heck algebra independently. They were thinking about super algebras. They showed that their super things were related to things like the spin symmetric group. More generally, this thing called like affine Clifford super algebra. Then these same guys with O constructed two representations on these things. And we needed that as well. But those guys were the building blocks. They helped us connect to things like the symmetric group. And at the end of the day, what you have is a story where this odd weirdo two category is acting on something that's related to the spin symmetric group. We proved that you get these new equivalences by copying Chuang and Rouquier. What those equivalences are doing are relating certain blocks of the spin symmetric group. So if you haven't thought about this, the spin symmetric group, this goes back to work of Schur. It's related to the double cover of the symmetric group, and this controls representations that are like projective representations of a symmetric group. So we're able to prove that relate blocks that are related by these derived equivalences just so happen to be the blocks that you need to show are equivalent. Forgot one more important critical factor here was work of Kleshchev and Livesey. It couldn't have happened without this recent work. If you're familiar with the Chuang and Rouquier story, there's this Chuang-Kashiwara-Tsuchioka step where they basically reduce the abelian defect conjecture to showing that certain blocks of the symmetric group are derived equivalent. So if you know these blocks are equivalent, then you can prove this conjecture. This conjecture sets up like defect groups and Brauer correspondence. The way that Chuang and Rouquier proved, they just showed certain blocks are equivalent. So we needed that analog of the Chuang-Kashiwara-Tsuchioka step. And that's exactly what these guys just did very recently, very conveniently as we were finishing our paper. So we could utilize their critical analysis to actually deduce the abelian defect conjecture, building on all these guys' work. So that's what's new. And I hope that I convinced you that this odd world is cool and there's lots of stuff left to be explored.